LearningMeasure.tv, science and engineering podcast with emphasis on measurement. Brought to you by David Archer and LearningMeasure.com. Episode 18, Measuring the Cosmos Revisited. Hello, I'm David Archer. I'm the owner of LearningMeasure.com and LearningMeasure.tv. This podcast is sponsored by TradePubcom, GotoMeeting.com, and is part of the Blueberry community of podcasts. LearningMeasure.com is a subscriptions-based training website where after a 2-week free trial period, you can have access to all the courses that were put together for a $5 a month subscription that pays for the courses and this podcast and everything we're trying to do. Okay, since I've decided to cut short that series on antenna measurements, I thought it might be a good time to revisit the material that was covered in episode 6. If you remember in episode 6, something went wrong and I didn't realize it, and the audio didn't go out with the podcast. So it seemed like this would be a good time to revisit that. Okay, so basically the topic today is how do you measure the large scale structure of the universe, and basically what the universe is doing as a whole. Now, if you go all the way back to episode 5, we had started working up to how to measure the solar system, how to measure the distance to the moon and the sun and all that. We're not going to go over that. If you want to go over that, review episode 5. And if you have any questions, maybe if you want some clarifications, ask and we'll try to clarify it. So we'll start out with the concept of a parsec, which was in episode 5. So like here's the sun, and you have the orbit of the Earth. And if you draw a line through the sun, and you have some star out here that's relatively close, you can look at the angle. You look at the stars, and then look at the star 6 months later. Once you know the distance of the size of the Earth's orbit, and that was explained in episode 5, a star whose this angle change in the sky is 1 parsec, is one arc second, is what's called 1 parsec away. Now 1 parsec equals, better look at this right, make sure I get it right, 3.26 light years. In other words, it takes 3.26 years for light to travel 1 parsec. Because of the angular accuracy achievable from the ground for parallax measurements, which is about 0.02 arc seconds, the limit that this type of measurement is about 50 parsecs. There's a lot of stars in 50 parsecs, or 163 light years. But the current state of the art with spacecraft and the like is and this is basically a direct measure of the distance to nearby stars, is 150 parsecs. So anything 150 parsecs is the limit, which is 489 light years. So in a sphere around the Earth of 489 light years, we can directly measure, just with geometry, the distance to the nearby stars. Well, what if you want to measure farther than that? Because, well, first of all, there's some other things you can tell from this. At 150 parsecs, we can't tell the distance. The star will not move in the sky if it's relatively slow. So the stars aren't moving so fast since there's lots of fixed stars, and they have a speed limit of the speed of light. So we're not too much farther we have to go before we run into that limit. So, so for stars to appear stationary, they have to be greater than 150 parsecs, and then a transverse velocity less than 0.006 arc second deflection per year. So there are stationary stars. Now that we have talked about how you can measure the closest nearby stars, we got to figure out how to measure a little bit further. Before we do that, we got to pay some bills. If you're looking for a better way to present or collaborate during your conference calls, your solution is simple. Web conferencing with GoToMeeting. During your call, everyone logs on to GotoMeeting.com and your computer screen shows up on their computer screens. It's like you're all in the same room. GoToMeeting is perfect for sales or product demos, training or real-time collaboration, plus you're not charged per minute like other providers. You can meet as often as you want for as long as you need. With GoToMeeting, you can meet with anyone, anywhere, without ever leaving your office. You'll not only save time, but money too. See for yourself. Try GoToMeeting free for 45 days. Just visit GoToMeeting.com/podcast. That's GoToMeeting.com/podcast. Try GoToMeeting today. Who knows, maybe someday you'll have meetings for the closest stars. Okay, now that you have a star, let's talk a little bit about the propagation of light from stars. Again, you have some star, and we've talked about this before. It's luminosity, it's power that it's putting out, and we want to look at that, the power delivered to a sphere of radius r. So the surface area of this sphere is 4 pi r squared. Okay, that's the surface area. Well, the power per unit area hitting this sphere is something you can, that you could measure at any point on this sphere. Is the power, luminosity, we'll call that L, of the star, divided by the surface area, 4 pi r squared. We'll call that S. So that's the power per unit area at incident on a point. Well, the important thing is that this S here, you can solve for R. So if you take S, S over L, L over S, divided by 4 pi, square root of that is R. But, see, this is something we know. This is something we may not know, but we can know for the closest stars. So we have some way of measuring distance. The important thing is it's basically a function of the total luminosity of the star and the measured power per unit area. This is something we can measure from Earth. We need to know that. Well, it turns out, the luminosity, turns out there's a class of star, and there are several of these stars within our limit of parallax measurements called Cepheid variables They're a variable star whose luminosity can be related to the period of the oscillation of the star. So once you have that, you have what's a standard candle, kind of what they call it. So once you know the relationship between a period and luminosity of a star, of a Cepheid variable, you can compute the distance basically using this formula to any observable stars of this type. Well, since there are several stars within the 150 parsec limit, we're able to calibrate this very well. And also, fortunately, the Milky Way galaxy has a couple companion galaxies where these type of variable stars that we're talking about exist and can be resolved. And doing this measurement on these galaxies are the Large Magellanic Cloud and the Small Magellanic Cloud. Doing this calculation on Cepheid variables on these two galaxies, we find that the Large Magellanic Cloud is 51,000 parsecs away, or 168,000 light years away. So a couple things we know. We know now the distance to the Large Magellanic Cloud. We know something else. We know that the universe has to be at least 168,000 years old as a minimum, because it would take that long for light to get here from there, and we can see the galaxy. Therefore, the universe is at least 168,000 years old. Okay, Small Magellanic Cloud, turns out it's 61,000 parsecs, or about 197,000 light years. And again, that shows that the universe is at least 197,000 years old. Now, an interesting thing that you might find is that the Andromeda Galaxy is one of the few galaxies that's moving directly at our galaxy. In fact, it's on a collision course. It's nothing we have to worry about. It's probably nothing the human race ever will have to worry about, because they probably won't be here that long. It'll be whatever the descendants of the human race become, but if they're around. But it's on its collision course with the Milky Way. But other than some of the local galaxies, there's some other interesting things that we can determine the speed of the galaxy towards us through Doppler shift. We've talked about that before. But once you get too far out, you can't resolve the Cepheid variables anymore. And you got to come up with some other way of doing this. But the other thing about the Andromeda Galaxy, we've measured that distance the same way, and it comes out to be 2.5 million light years away. So again, the universe has to be at least 2.5 million years old, because we can see that galaxy, and its distance is at least 2.5 million light years away. Once you have some galaxies that you can calibrate their average brightness, you can use that in this type of formula. And so you could look at the average brightness of a galaxy. So you can use the brightness of galaxies to estimate the size of the universe. And the farthest galaxies we've ever seen was in the Hubble Deep Field image. And the universe is pretty amazingly large. But before we finish up, we've got to do one more thing.
One of LearningMeasure.tv's sponsors is TradePub.com. TradePub.com is a site where one can sign up for a large number of free trade publications. If you'd like to support this podcast, go to the LearningMeasure.tv site, scroll down to the free publications link, and choose one of the magazines or one of the publications or one of the categories, and sign up through that link. Each publication subscribed to through this link on learningmeasure.tv website helps keep Learning Measure TV on the air. Thank you for your support.
Okay. There's, in previous episodes, we talked about Doppler shift. With Doppler shift, you can measure the velocity, basically, the relative velocities of galaxies. Because we know what atomic structure looks like, we know what spectral lines look like, we know where they should be, we see them shifted, therefore we can know the velocity of galaxies and stars, measuring Doppler shift. But now we know something about distance, we can ask the question, well, how is the universe moving? Well, it turns out that if you plot measure distance to the galaxy and to a galaxy versus its velocity, it turns out you get something that looks like that, a straight line. This is called a Hubble diagram. Actually, here's one that's has some data on it. But as you can see, the velocities seem to be a linear function of the distance. So the universe is, at least on some average sense, expanding fairly uniformly. Since you can see that the galaxies are moving further apart, you can sort of imagine that if time went backwards, they're getting closer together. And at some point, it all collapses to a point. This observation implies that at least the universe as we know it has a finite age. And through various ways to estimate this age, the current estimate of the age of the universe is 13.7 plus or minus 0.2 billion years. Pretty old universe. But actually, so it's kind of interesting in a way, is if you look in more detail, the current thing is that the universe is not uniformly expanding, but rather its expansion is accelerating, which is truly mind-boggling. Well, maybe not so, but which has some interesting long-term implications for the universe. The universe is tearing itself apart, basically. Eventually, atoms will pull themselves apart even, but that's way distant future. Nothing that we have to worry about, or any of the human race probably will ever have to worry about. Anyway, that's all I wanted to talk about on this, redoing some of the stuff that was on episode 6. I really would like some input on where you'd like to see me go with this. I would prefer to do some measurement-related thing, but I can cover anything that you guys are interested in. So if you have any suggestions on what you'd like to see, send me an email at suggestions@learningmeasure.tv. If you'd like to be on the show, promote your product, promote yourself, send me an email at vendors@learningmeasure.tv. And if you have any questions at all, homework question, engineering question, philosophical question, personal question, I might take a shot at trying to answer it on the air, depending on whether I think it would be relevant or not. Okay, that's it for now. I'll try to come up with something for next time.